All right, well, hello everyone, and welcome back. In this video, we will revisit some of our favorite DC tools and use them to solve AC circuits. So we'll cover how we can use source transformation, superposition, Thevenin Norton equivalence, and op-amps in AC circuits. This lecture is one of my favorite of the semester because we get to see how all our favorite DC tools still work with AC circuits. And often, when we see these tools for the second time, things make a lot more sense. Alright, so in this video, we'll briefly review what we've covered so far about AC circuits, and then we'll cover how to use source transformation, superposition, Thevenin Norton's theorem, and AC op-amps using AC circuits. And we'll see that a lot of our favorite techniques in DC circuits carry directly over to AC circuits with very minimal differences. So let's briefly review what we've covered so far. So in our past few videos, we have learned how to solve typical AC circuit problems. Generally, we follow this procedure. We first transform everything from time domain into frequency domain. So to do this, we write all our currents and voltages as phasors, and we need to find the impedances of all the components using our favorite impedance equations. Once we've found our impedances, then we use them, resistor style, to determine the desired unknowns in our circuit. Then, once we have found our solution in frequency domain, we transform our solution back into time domain. So if you'd like further review on this process, I'd highly recommend that you check out some of our earlier videos on AC circuits. Let's just briefly review the impedance equations that we've covered. So remember, if we want to convert resistors, capacitors, and inductors to impedance, we need to use our favorite very important equations. And, of course, the math relation 1 over j equals negative j is also really useful. So definitely keep these equations handy, because we're going to continue to use them throughout the rest of this course. Once again, if you'd like further review on how to use these equations, check out our earlier videos. So in our last video, we covered some good news. In our last video, we learned that we already know the tools we need to solve uglier AC circuits. And in our previous video, we had started applying our favorite DC tools to AC circuits. In the previous video, we looked at voltage and current division, equivalent resistors, Ohm's law, and node and mesh analysis. So check out our previous video if you want to see those. In today's video, we're going to focus on these remaining tools. We're going to see that to solve AC circuits using these tools, we use the same process we already know with only minor changes. The main differences are that we must first express our AC circuits in frequency domain using phasors, and we have to express our components as impedances instead of resistance, inductance, or capacitance. Once we have transformed our AC circuit into frequency domain, we can use our favorite DC tools pretty much the same exact way. So in the rest of today's video, we're going to go through each of these tools and demonstrate an example of how we can take our favorite DC tool and use it now in an AC circuit. Before we move on, let's cover a few more helpful tricks as we solve more AC circuits. In our previous video, you'll remember I introduced this box trick. This is not an official name, this is just something silly I made up. But often it's very helpful to use this trick after you have converted your circuit to frequency domain. Remember, in the box trick, all we're doing is we redraw our inductors, capacitors, and resistors as boxes in frequency domain. The advantage of redrawing these components as boxes is that it makes it easier for us to combine these equivalent impedances together. So once you've replaced your impedances with boxes, you can treat each rectangular box like a resistor and perform circuit analysis as usual. So you do not have to use this box trick, but for me personally, I find it unintuitive to combine inductors, capacitors, and resistors together. For me, it's a lot easier to combine them if they all look like boxes. So please use the box trick if you find it helpful. There's one other additional trick that I would like to share that is helpful for completing complex number calculations. In today's examples, we're going to be doing a lot of conversion between rectangular and polar form. And most of the time, if we're just doing homework, we can use the online phasor calculator. But you still need to know how to do the hand calculations yourself on exams. But sometimes there's some shortcuts we can recognize that will make this conversion faster. So here's a few special cases to be aware of. If you have a completely imaginary number with no real parts, remember that number in rectangular form will be written as j times the value. And in polar form, since that number is completely imaginary, we can just write it as b angle 90 degrees, where b is that complex number's value. Remember, this is the case because on the complex plane, the imaginary numbers, if you're completely imaginary, your real component will be 0, and our phase angle theta will be 90 degrees. Similarly, if our number is completely real, with no imaginary parts, notice we end up with the number having theta being 0 degrees, because the number lives only on the real axis of our complex plane. So if we have a completely real complex number, we can quickly write it in polar form as a angle 0 degrees, where a is the value of the real number. One other helpful trick is, you'll remember if we have a negative sign in front of the amplitude, we typically write our amplitude as a positive number since it is basically our distance from the origin. So if we need to change our sign, remember that's essentially just rotating our phase angle theta by 180 degrees. So if we need to change the sign of a phasor in polar form, all you need to do is rotate that phase angle by 180 degrees. Remember, don't be afraid to double-check your work using the online phasor calculator on homework problems. Make sure you understand how to do these calculations yourself without the calculator in preparation for exams. All right, so before we move on, let's do one last review question. And we're going to return to this circuit a little bit later when we cover superposition. Notice in this circuit we actually have two sources. We have one source, V1 of t, and we have a second source, V2 of t. So here we are being asked to convert the circuit to frequency domain. Notice this extra bit. Be sure to determine impedance at both frequencies. So notice what's happening here. We have two sources, and in this case, V1 of t has omega equals 50 radians per second. And notice, V2 of t has omega equal to 10 radians per second. And also remember that the impedances of our inductor and capacitor, these impedances are frequency dependent. So you'll remember, impedance of an inductor is J omega L, impedance of a capacitor is 1 over J omega C. So you'll notice in this case that depending on which frequency we are operating in, the impedance of the inductor and the capacitor will be different. For now, let's focus on just determining what these impedances are, and a little bit later in the video, we'll return to this question and apply superposition. So let's go ahead and convert everybody to frequency domain. So in this case, we can go ahead and start with our voltage sources. V1 of t will turn into a phasor operating at 50 radians per second. Notice here, it's a good idea to keep track of that frequency because we have two different frequencies in this circuit. So our V1 of t is going to be just written in polar form as A angle theta. So here we get our A is 20, theta is 0 degrees. And notice V2 of t gets converted to V2, but notice the frequency is different. So even though these phasors have the same amplitude, same phase angle, just remember the frequencies are different. So later during the superposition calculation, we have to make sure that we use the impedance at the correct frequency when considering each source alone. Let's go ahead and find the impedances now. Let's start with my favorite. Impedance of our 8 ohm resistor? Well, that one's easy. That one is not frequency dependent, it's just equal to the resistance. But then we have to be a little careful about our two frequencies. So let's go ahead and write down both of them. If our omega is 50 radians per second, then we know the impedance of our capacitor is 1 over J omega C, which is 1 over J times our omega being 50, and our capacitance C being 2000 times 10 to the minus 6 farads. That gives us minus J10 ohms. if we're at 50 radians per second. But if we're at 10 radians per second, notice what happens. Notice now we're multiplying our denominator by 10, and for the 10 radian per second case, we will end up with minus J50 ohms for that capacitor's impedance. And then similarly for the inductor, notice we end up with J times 50 times our impedance or our inductance in henries, which is 0.15. So we get J 7.5 for our inductance turning into impedance. But for our 10 radians per second, notice we get a different number. So for now, we have successfully converted this circuit into frequency domain. We know what our voltage phasors will be, and we know what our impedances are at both frequencies. So later, we will revisit this circuit and find that voltage V8 ohm as a function of time using superposition. So by now, converting circuits to frequency domains should be very intuitive. And hopefully you found this example pretty easy. If you're still having trouble, please be sure to review our previous videos, and feel free to reach out if you have further questions. Alright, so now that we're done with review, let's move on and first cover source transformation. You may remember this slide from our Lecture 6 video. In Lecture 6, we had learned that source transformation allows us to replace a voltage source and series resistor by an equivalent current source and parallel resistor. Notice that the requirement here is that in order to do that transformation, we must follow the source transformation equations shown here. And remember, the circuit must have linear behavior. So it turns out that source transformation also works with AC circuits. And we'll see that there's only two small modifications that we need to make. First, we use phasors instead of current and voltage. And then, instead of using resistance, we use impedance. Let's take a look at how source transformation works in AC circuits. You'll see the procedure is basically the same as what we had learned in Lecture 6. First, we just need to convert our circuit into frequency domain. So we convert our sinusoidal voltages and currents into phasors. And then, of course, we convert all the other components to impedances. Then, if needed, we apply our box trick and simplify. And finally, all we need to do is use our same source transformation relations to determine the desired current, voltage, and impedance. So our favorite equation for our source transformation resistance is now source transformation impedance. Just like with resistors, we see that the source transformation impedance will be equal for both series and parallel. And then our voltage and current phasors are related by a similar equation, except now instead of Rs and Rp, we have Zs and Zp for our impedances. One other thing to notice, that the voltage source and the current source must still point in the same direction after the transformation. So just like before, if we happen to have a voltage source that was pointing the wrong way, you'd still need to multiply by -1 if needed. In order to maintain the polarity of the source. All right, so let's go ahead and try a quick example. We'll see that the approach is just like what we already know for AC circuits. Here we are given a parallel current phasor and a parallel current impedance, or a parallel impedance. And we want to determine the equivalent voltage phasor and series impedance if we had done a source transformation. So here, we want to find Vs and Zs. And let's go ahead and remind ourselves from our source transformation equations, we know that Vs is going to be equal to IPZP, and Zs is going to equal to Zp by source transformation rules. So what is our value of Zs going to be? Well, that's the nice easy one, right? Our favorite relation still holds. Zs is just going to be equal to Zp. So we know Zs will be 174.8 angle 29.1 degree ohms, because that is what our Zp was. All right, then. Now we just need to find Vs. And we know Vs is going to be Ip times Zp. So we substitute. Ip was 0.18 angle 0 degrees amperes. Zp was 174.8 angle 29.1 degrees ohms. So be careful of units here. Remember, we need to be in amperes, ohms, and volts in order for our units to not be off. So this is nice and easy. We just multiply our magnitudes and add our angles. And we determine that our Vs value will be 31.46 angle 29.1 degree volts. And notice in this case, our polarity is pointing upwards for both. So there's no need to multiply this by -1. But if our Vs happened to be in the opposite orientation, then we would need to multiply by -1. So be sure to double check that you have indeed solved for the correct polarity and multiply by -1 if you need. All right, let's now move on to superposition. You'll remember, also from Lecture 6, that we introduced superposition for DC circuits. We learned that in any linear circuit containing multiple independent sources, the current or voltage at any point in the circuit can be calculated as the algebraic sum of the individual contributions of each source acting alone. So once again, here we are looking for independent sources and a linear circuit. It is still possible to have a circuit be linear and a source be independent, even if the source has some time dependence. So time-dependent AC sources can still be linear. And independent. Remember, a dependent source would be drawn with a diamond symbol, and nonlinear sources would have some sort of nonlinear relationship between our IV curve. So most of the time in this course, unless otherwise stated, we generally assume that our AC circuits have linear behavior. And again, typically, if we had nonlinear behavior, usually that's in cases where we have dependent sources or op-amps or other active components in our circuit. All right, so we're going to learn in this case that our favorite superposition tool from DC circuits also works with AC circuits. There's just a few modifications we need to make. First, like before, we use phasors instead of current and voltage values. We use impedances instead of resistance, inductance, and capacitance. And notice this last point. This is important. If we have multiple sources in our circuit, and if the sources operate at different frequencies, the impedances may be different. So we also have to be careful that if we're doing a superposition question, we need to make sure we use the correct impedance value at the same frequency of whatever source that we're looking at. We'll do an example in just a moment illustrating how this works. Before we do an example, let's briefly review the superposition procedure. And this is very similar to Lecture 6. So first step is we need to transform our circuit to frequency domain. And I also recommend applying the box trick to make it easier to simplify things. Then, just like with DC circuits, we need to consider each source separately. So we replace our independent voltage sources with a short or plain wire, and we replace the independent current sources with an open or broken wire. If there's any dependent sources in the circuit, notice that we do not change those. Once we have considered each source separately, we draw the circuit with each source alone, and we calculate the contribution of each source to the desired output parameter. You need to be careful when calculating these contributions. Here's a very important thing to note. Sometimes we will have superposition problems where the sources operate at different frequencies. So if your sources have different frequencies, when considering a source alone, make sure you use the impedance values at that source's frequency. So we'll do an example on the next slide. And remember, finally, once you have found the contributions of each source acting alone, then you take the algebraic sum in order to determine the total value of that desired parameter. So let's go ahead and take a look at an example of superposition in an AC circuit. So let's consider this example. And you'll see this is the same circuit that we looked at earlier in our review question at the beginning of the video. Here we are given our V1 and V2 voltage sources, and we want to find the voltage across our 8 ohm resistor. So in this case, we have two sources. Notice they are operating at those different frequencies, but we can still use superposition in order to determine the combined effect of the two sources on our 8 ohm resistor. Let's go ahead and apply our superposition procedure and see how this works. So let's go ahead and use superposition. And remember, the first step of our superposition process is to transform the circuit to frequency domain. And then apply the box trick. So we already did this frequency domain calculation earlier. So let's just take a look at what we have. Notice I'm just replacing my impedances with boxes here. And remember, in our earlier example, we saw that our impedance depends on our frequency. So our voltage source V1 is equal to 20 angle 0 degrees at our frequency omega is 50 radians per second. And under those conditions, we know that our capacitor will be minus J10 ohms. We know that our inductor will be J7.5 ohms. And we know that our 8 ohm resistor is just going to be 8 ohms. Similarly, we know that V2 is going to be equal to 20 angle 0 degrees with frequency 10 radians per second. And remember, we calculated that our impedances are going to be different at 10 radians per second. Resistor is still 8 ohms, but now, at 10 radians per second, the impedance of our inductor is going to be J1.5 ohms, and the impedance of our capacitor is going to be minus J50 ohms. So the key thing to watch out for is we need to make sure we use the omega equals 50 impedances for V1 calculations. And we need to use the omega equals 10 impedances for V2's calculations. And here I had color-coded those. Omega equals 50, I wrote in blue. Omega equals 10, I wrote in purple. All right, so we have now transformed everybody to frequency domain, and we've applied our box trick. Our next step is to draw the circuit with each source considered separately. And then what we can do is we can solve for each source's contribution to that voltage across our 8-ohm resistor. So let's go ahead and do that. Let's first consider the circuit with V1 of t alone. So notice we replace V2 of t with a short to turn it off, and we end up with this. So we've got our V1 source. We have our minus J10 impedance from our capacitor. We have our 8-ohm resistor. And then on the right, we have our J7.5 impedance from the inductor. And notice our V2 source is now replaced with a short. So here we want to solve for the voltage across the 8-ohm resistor with voltage V1 considered alone. And then notice we are using the impedance values for our frequency omega is 50 radians per second. So notice I'm choosing the values to match my source V1. Okay, well, how can we find the 8-ohm across the 8-ohm resistor? Do we have any tools in our toolbox that would be helpful here? One thing that's helpful to notice is that the 8-ohm resistor is in parallel with the J7.5 ohm, or let's call these impedances. 8-ohm impedance is in parallel with the J7.5 ohm impedance. So we can combine. We can combine into an equivalent impedance where that equivalent impedance is equal to our 8 ohm in parallel with J 7.5 ohms. So we can use our shortcut equation. Here we know that the 8 ohm resistor, that will just be 8 angle 0 degrees. Then we have our 7.5, J 7.5 impedance, that is going to be 7.5 angle 90 degrees. And we divide by 8 plus J 7.5. We'll go ahead and use our online phasor calculator here. So we'll go ahead and convert 8 plus J 7.5. That becomes 10.96 angle 43.15 degrees. And so if we go ahead and simplify this, we determine our Z equivalent will be equal to 5.47 angle 46.85 degrees. And I'm also going to proactively write it in rectangular form as 3.74 plus J4 ohms. I highly recommend that you try going back through this calculation yourself and make sure you can get the same result that I did. Alright, so now remember our goal is to find the voltage across that 8 ohm resistor, which happens to be the voltage across our impedance. So how do we get this? Now that we know our Z equivalent impedance, we can use Kirchhoff's voltage law or voltage division. Let's go ahead and try voltage division. We know that the voltage across the 8 ohm resistor, that's going to equal Z equivalent divided by Z equivalent plus negative J10 ohms times our source, which was 20 angle 0 degrees volts. So if we go ahead and simplify that, we'll get 5.47 angle 46.85 degrees divided by, the C equivalent is 3.74 plus J4. We subtract minus J10, we get divided by 3.74 minus J6 times 20 angle 0 degrees. We need to write the 3.74 minus J6 in polar form. So if we convert that to polar form, we get 7.07 angle negative 58.06 degrees. And finally, if we go ahead and math that through, we determine that our voltage will be equal to 15.46 angle 104.91 degrees volts, or in sinusoidal form, that gives us 15.46 cosine. Notice we have omega's 50 here, so we get 50t plus 104.91 degrees. So now we have successfully completed the calculation for the voltage across the 8 ohm resistor with V1 alone. We now need to repeat this process for our source V2. So we're going to go ahead and repeat our calculation, but now we consider V2 all by itself. So if we do that, notice now V1 gets replaced with a short, and we are left with the following. So once again, notice here, we are using the impedances for the omega equals 10 radians per second now, because our source V2 operates at 10 radians per second. Another thing you can notice is we can use the same procedure as before. We can notice that our voltage we're trying to find that voltage is the voltage across the 8 ohm in parallel with the minus J50 ohm. So what we can do is first replace the negative J50 ohm and 8 ohm with an equivalent source, the equivalent, and then we can use voltage division. So same procedure as before can be used to find the voltage across the 8 ohm resistor with source V2 alone. So if we go ahead and do that, we determine our Z equivalent is just going to be 8 ohm resistor. Notice now we have that negative sign again, so we do have to watch out for that, because the capacitance has a negative value. We have negative 50 angle 90 degrees. Then we divide by 8 minus J50. This gives us 8 angle 0 degrees. That negative 50 angle 90, I'm just going to go ahead and proactively replace it with a negative 50 or positive 50 angle negative 90. So this is just to get rid of the negative sign. I'm just going to rotate my theta 180 degrees. So you could either add or subtract 180 degrees here, as long as you just rotate it to get rid of that negative sign in front of the amplitude. That could also be done at the end of the calculation, but I prefer to just do it before I forget. Down below, 8 minus J50, that will convert and become 50.63 angle negative 80.91 degrees. So if I go ahead and do this math, I will determine that my Z equivalent will be equal to 7.90 angle negative 9.09 degrees, or in rectangular form, 7.80 angle, or I'm sorry, minus J 1.24 ohms. So we found our Z equivalent value, last step is to do voltage division. And if we do our voltage division with our Z equivalent and our 1.5 ohm, J1.5 ohm impedance, we get the following. And this whole thing simplifies. And finally, we determine that our voltage, the 8 ohms across the resistor from source V2, we get 20.24 angle negative 10.94 volts. And if we write that in sinusoidal form, we'll get 20.24 cosine 10t minus 10.94 degrees. So notice this time, since we were working with source V2, we had to use 10 radians per second as our frequency. All right, so finally, our last step is to complete the superposition by adding the algebraic sum of each source considered separately. So in this case, we know that the voltage across the 8 ohm resistor must be equal to the sum of the two sources acting alone. Notice we're asked for the final voltage as a function of time, so we do need to add our cosine forms of the voltage for this answer. So we go ahead and substitute everyone in, and we determine the following. And there you have it. So this solution is actually very interesting because, in fact, we end up with something where we have the two waves superimposed on each other where one is higher than the other. And we actually end up getting a result something like this, where we get the 8 ohm of T will have the two sinusoids superimposed on each other in the final result. All right, so there you have it. And you can see that superposition with AC sources really isn't that bad. The key thing to watch out for is if the frequency of your independent sources is different, make sure you use the impedance for each source at its correct frequency. All right, so let's now continue on with Thevenin's and Norton's theorems. You'll remember from Lecture 6 that Thevenin's and Norton's theorem allow us to replace an ugly circuit that we don't like with a much simpler equivalent circuit. So we can basically take some ugly circuit that we don't like and replace it with either a voltage source and series resistor or a current source and parallel resistor. And remember, Thevenin's theorem tells us that we can do that replacement to get voltage source, series resistor. The voltage of that source will be our Thevenin voltage. Resistance of the series resistor is Thevenin resistance. Similarly, the parallel current source is our Norton current, and the parallel resistance is our Norton resistance. So we learned that this is really helpful for DC circuits, and it's also going to be really helpful for us in AC circuits. And it turns out that when you want to use Thevenin's and Norton's theorems with AC circuits, you basically follow the same approach that we already know. You'll just notice a few minor changes. First, our Thevenin voltage becomes the Thevenin voltage phasor, and Thevenin impedance replaces our Thevenin resistance. Similarly, the Norton current is replaced with a current phasor, and the Norton impedance replaces the Norton resistance. But still, as we learned with source transformation, we can convert easily between Thevenin and Norton using a source transformation. So let's briefly review how to find Thevenin and Norton equivalent for AC circuits. Alright, so as usual, we first convert the circuit to frequency domain, and then we follow the same approach we already know to find Thevenin voltage and Thevenin impedance. Remember, to find Thevenin voltage, we just need to find our open circuit voltage across the open terminals. Our Thevenin voltage is equal to the open circuit voltage phasor. Then for Thevenin impedance, it's just like what we learned in DC circuits. If we have no dependent source, we replace voltage sources with shorts, replace independent current sources with opens, and then we find our equivalent impedance. If we do have a dependent source, remember then we need to connect that external source and find VEX over IEX, and then we can determine our Thevenin impedance using VEX divided by IEX. So this procedure is very similar to what we learned in Lecture 7. If you'd like further review on how to calculate Thevenin, I'd highly recommend you check out Lecture 7 to 8. Let's go ahead and do an example of how to find the Thevenin equivalent. So here we are given this circuit already transformed into frequency domain. Remember, if you were given something in time domain, you would just need to convert. And so here we are asked to find the Thevenin equivalent for this particular circuit. Let's give this a try. So remember, our first step is to convert to frequency domain and apply the box trick. This was done for us. Definitely make sure that you're comfortable enough to do that calculation on your own. Our next step is to find our Thevenin voltage. We know that's equal to our open circuit voltage, VOC. How can we find VOC in this circuit? If you'd like, pause the video and see if you can find it on your own. Otherwise, let's try it together. In this case, one strategy would be to combine the 80 ohm and J80 ohm resistors and then use voltage division. So if we do that, let's see what we get. So notice here, we're going to combine our two impedances, 80 ohm, J80 ohm, since they're in series with each other. And of course, our VOC is now equal to the voltage across that combined impedance. So using voltage division, we determine that VOC, or our Thevenin voltage, is equal to our 80 plus J80 ohm impedance divided by 80 plus J80 minus J20, the whole thing multiplied by 5 angle negative 30 volts. If we simplify this and convert various components to polar form for addition, we'll end up with 113.137 angle 45 degrees on top, divided by 100 angle 36.86 degree ohms on the bottom, times 5 angle negative 30 volts, and we'll end up with VT equaling 5.657 angle negative 21.87 degrees volts. So notice, now that we are in frequency domain, our Thevenin equivalent will be written in terms of phasors and complex numbers. So we found our Thevenin voltage. Let's now finish up by finding our Thevenin impedance. Notice here the question did not specify which format to write our Thevenin voltage. It didn't say time domain or frequency domain, so we'll just leave it in polar form, but if we needed, we could also have converted our Thevenin voltage back to a sinusoid. So let's go ahead and find our Thevenin impedance. And so notice in this case, we don't have any dependent sources. So what we need to do in this case is we replace our voltage source with a short. If we had a current source, it would be replaced with an open. And then we find the equivalent when walking across the open terminals. So in this case, our voltage source gets replaced with a short. And notice now all that's left is we have that minus J20 ohm impedance up top, and we have an 80 plus J80 ohm impedance on the right. So notice I need to find the equivalent impedance when walking from A to B. And so we see that in this case, the two impedances are in parallel with each other. So our Thevenin impedance will just be whatever the parallel value of those two impedances is. So in this case, if we simplify, we'll get negative 20 angle 90 degrees times 113 angle 45 degrees divided by 100 angle 36.87. Notice I have a negative again, so in this case I'm going to rewrite that as 20 angle negative 90. Rotate that phasor by 180 degrees. And all I need to do now is just multiply the top, divide by the bottom. And if I do that, I determine that my Thevenin impedance is going to be 22.628 angle negative 81.87 degrees ohms. So as you can see, the Thevenin procedure is just like what we already know for DC circuits. The only difference is we need to use phasors and impedances when solving these problems. Alright, our last topic for today is AC op-amps. And it turns out that those golden rules we learned back in Lecture 9, these still apply. And so the only difference is we use phasors and impedance when working with AC circuits. For now, we will introduce two general types of AC op-amps. You'll remember these are very similar to the ones we covered back in Lecture 9 and 10. And so basically, instead of having resistors, we now have impedances in these op-amps. And so I do not expect that you memorize how to draw these, but I do expect that if you see one of these in a homework problem or an exam question, I expect that you would be able to recognize that these are inverting and non-inverting amplifiers, and I would expect you to know which equations to use. So for AC op-amps, we often care about the ratio of the output to the input voltage, basically our gain. And we can show, if we use node analysis similar to Lecture 9, we can show that we would derive these equations. So for an inverting amplifier, we see V0 divided by Vs is just negative Z2 over Z1. And for non-inverting, we have V0 over Vs is Z1 plus Z2 divided by Z1. So the general strategy is to first recognize which type of amplifier you have, and then you use the corresponding equation in order to determine V0 over Vs. Let's go ahead and try a quick example before we end for today. So in this example, we are given an op-amp, and we know our input voltage. We're also allowed to assume this op-amp is ideal so that we can use the equations we just learned. First question asks, what kind of amplifier do we have? And the second question asks us to find V out as a function of time. So notice this should be written in sinusoidal form because it's time domain. All right, so what kind of amplifier circuit is this? Well, we don't have a circuit with a capacitor in it, necessarily, but notice the capacitor and resistor here are parallel with each other. So in fact, in this case you can see that we must have an inverting amplifier. Another trick is to look at where the voltage input is, and you can see that for the inverting amplifier, our voltage enters at the negative terminal. For non-inverting, our voltage input enters at the positive terminal. So, by the reasoning we discussed, we can conclude that this is an inverting amplifier. And now all that's left is to determine our output voltage as a function of time. And in order to do that, let's use our equation that we just learned. We know the ratio of the output to input voltages for an inverting amplifier will be negative Z2 over Z1. So in this case, we know that our V out over Vs is going to be negative Z2 over Z1 for the inverting amplifier. So in this case, notice Z2 is the capacitor and 20 kilo ohm resistor in parallel with each other. And notice Z1 is just equal to 5,000 ohms. So in order to find that ratio, we need to find Z1 and Z2. So let's find Z2. We know that it's just those two components in parallel. And again, watch the units here. I'm going to convert kilo ohms to ohms just so I don't mess anything up. And we can determine in this case that the 0.1 microfarad capacitor, that is going to have an impedance of negative J20,000. And of course, a 20 kilo ohm resistor is just going to be 20,000 ohms. And notice here again, I can determine the J20,000 from 1 over J omega C, where omega is 500. So in this case, if we go ahead and simplify that, we get J20,000 times 20,000. Oops, sorry, negative J20,000. Don't forget that negative sign. And that is divided by negative J20,000 plus 20,000. So if we go ahead and simplify this whole thing, I'm going to convert the numerator to polar form, and so we'll actually end up getting negative 20,000 angle 90 degrees times 20,000 angle 0 degrees divided by this bottom portion will become 28,284 angle negative 45 degrees. So we determine Z2 will ultimately equal 14,142. In this case, I'm going to leave my negative in front of there for now. Just notice I have the negative there. Because you'll notice that this negative sign on the Z2, that's going to get canceled out when I plug it in to that V0 over Vs equation. Otherwise, if I wanted to, I could just add 180 degrees or subtract 180 degrees to get rid of that negative sign. All right, so now that we know that, we can just say that V0 over Vs must equal negative Z2 divided by Z1, which means V0 must be equal to negative Z2, which is 14,142. So notice the negative signs cancel. And then Z1 is just 5,000 angle 0 degrees. And we're multiplying all that by our voltage source, which is 2.4 angle 0 degrees. If we do all that math, we determine that V0 is equal to 6.78 angle 135 degrees. And as a function of time, that will give us 6.78 cosine of 500t plus 135 degrees volts. So notice that these op-amps questions are very, very similar to what we already learned in DC circuits. Key thing is to make sure you pay attention to sign errors and ensure you do the phasor math correctly. All right, let's go ahead and wrap it up here for today. I hope you enjoyed taking this look one more time at our favorite DC tools and seeing once again how they can be useful for AC circuits as well. It's often really satisfying to go back and revisit these tools, and now that we know them for DC circuits, it's pretty satisfying to be able to use them again in AC circuits. Next time, we'll take a closer look at frequency response and phasor diagrams, and then we'll start talking more about AC power. Thanks everyone for joining the fun. Feel free to reach out if you have any questions, and we'll see you in the next video.